All right, gonna go over just a couple examples here. How do we turn alcohols into alkyl halides? Um, Very useful because you're replacing a bad leaving group with a good leaving group. So your book talks about, okay, there is a way that we can just use really strong hydrobromic acid, really strong hydrochloric acid, and you can make an alkyl halide out of alcohols. But for a lot of reasons, these things aren't really that good, okay? The first example provides us a primary alcohol. We know it's going to perform an SN2 reaction, but notice, okay, in order to do that, we need heat. So our product isn't going to be that pure. We're going to get some elimination product out of that. Even though Br minus isn't a great base at all, if we add heat, it's going to favor some of that elimination product. So it's not going to, I think it gives something like 76%. And not only that, we have to wait 4 hours to actually get it, okay? So even an SN2 is not that great. If we try it under an SN1, okay, I added water here as a protic solvent just to show it's SN1. Notice our products, because we're SN1, we get a carbocation intermediate. We have front and back side attack on an sp2 carbon, which is planar. Therefore, we get two products instead of one, which is not great for synthesis. We also are susceptible to a carbocation rearrangement. Okay, so if I add a methyl group there, my carbocation can shift, and now I've replaced my substituents in a different location. Maybe that's not all that bad. It's not usually going to show up in a synthesis, however. So it's susceptible to carbocation rearrangements. You get multiple products. It can take a long time. You need to add heat. You're not getting a very pure product. So instead, what we usually use is PBr3 and PCl3. Okay. We haven't gotten to SOCl2 yet, I don't think. So we don't need to worry about that one. But these are a lot better. They are stereospecific, meaning they're not going to give a range of stereocenters here. They're only going to give one stereocenter. They're not susceptible to carbocation rearrangements. And they can also occur in mild conditions, whereas these were really acidic up here. We can perform these in a lot more mild conditions. So let's go through the reactions of both of these, replacing an alcohol with an alkyl halide, okay? Our first step here, I'm going to write out phosphorus. Try them on your own, of course. Pause the video, see if you can go ahead and do these. It would be great. Very likely to show up on the assessment on Monday. I'm going to write out PBr3, the structure. Okay, sweet. Our first step is going to be our oxygen bonding. Who has electrons? Oxygen. Who wants them? Phosphorus, right? It's three bromines pulling electronegativity away from it, okay? So big partial positive on our phosphorus, and that is where our oxygen is going to bond to, okay? Phosphorus making 4 bonds isn't that good. Bromine's a good leaving group. We're going to go ahead and push off one of our bromines as well, leaving us with an intermediate that looks like stereocenter doesn't matter. The stereocenter with both of these, the intermediate steps, it's not going to be a big deal. Your final step, it's just going to flip, okay? Yeah, it's going to go through an SN2 reaction at the end, so we know it's just going to, if it's a wedge, it's a dash, if it's a dash, it's a wedge. Our intermediate, I'm just going to keep as a wedge. That's what I was wondering about there. Oxygen, hydrogen, phosphorus, Br2, okay, and Br minus. This is really funky because we're drawing these mechanisms out, which we don't always really do in synthesis. This is a little funky looking here. And we have a positive charge on oxygen. Just like on water, we had a positive charge. It was a good leaving group. Hey, wouldn't it be great if we could just make this group leave an oxygen making 2 bonds rather than 3? Good leaving group, great nucleophile. SN2 reaction here. Flip the stereochemistry with backside attack. And now I get as a final product this, only this, no elimination, not the other Steri-Center, in mild conditions. So much better way of adding a halide and replacing in place of an alcohol. Okay. Final product there. I also got that weird OHPBr2 kind of thing here, and I think that's all we made. All right. One more thing with this. Here's your answer. One more thing with this. The only thing this thing is actually susceptible to is, okay, we had that large kind of intermediate, that PBr2OH group. So it is susceptible to steric hindrance. It's not going to go on tertiary carbons. That's pretty much it. Okay, it might, but at really low percentages. So your book provides this example here, and it's like, okay, go ahead, see what you can do with it. What's going to happen? What we just did up here is going to be the same as at this position. Okay, sp3 hybridized. It's on a secondary carbon. That's okay. This one here, it's going to be very unlikely. Maybe we get a little bit, but it, for a final answer, okay, only has a chlorine here, okay, and then we also flip that stereochemistry. So as our final answer for this one, and again, we don't need to always draw mechanisms for these. A lot of synthesis we don't. We just write our final product. Our final product would look like that. We don't replace that alcohol because it's in on a tertiary carbon, okay, sterics. That's pretty much it there. So the only thing it's susceptible for, it's not really likely to attack that bulky area, just because it is kind of large. But otherwise, use that instead of using a really concentrated acid to achieve the same thing. Main thing there. Next video will be on epoxides. Keep going with your study guide.